and self-introduction in it. Please don't off the presentation mode and kindly pin the speaker's screen to view his presentation. At the end of the session, the feedback form link will be posted in the chat box. Attendees will receive the participation certificate only after submitting the feedback form. Now I request Mr. Hemachandra to address the opening note.
Yeah, thank you, Kavita. It's a great pleasure for me to welcome you all to this international webinar conducted by IEEE Control Systems Society of the Electronics and Instrumentation Department from St. Joseph College of Engineering, Chennai. The engine of this webinar is Professor Shreyas Sundaram, who is here to present the lecture on resilient distribution coordination in large-scale network. Professor Shreyas Sundaram is an associate professor in the School of Electrical and Computer Engineering at Perth University. He received his PhD in electrical engineering from the University of Illinois. He was a postdoctoral researcher at the University of Pennsylvania and was an assistant professor at the University of Waterloo. His research include network science, the application of algebraic graph theory to system analysis, and many others. Dr. Sundaram is a recipient of the NSF Career Award and an Air Force Research Lab Summer Faculty Fellowship. He received an award for his outstanding mentorship of engineering graduate students. He was also honored by the HKN Outstanding Professor Award, the Hesselberg Award for Teaching Excellence, and the Ruth and George Spira Outstanding Teacher Award. At Waterloo, he received a research award in the Department of Electrical and Computer Engineering, Outstanding Performance Award in the University of Waterloo, and the Faculty of Engineering Distinguished Performance Award. Hence, it's obviously a wonderful opportunity for us to hear from such a great personality. Thank you, sir, for joining us today. The session is yours.
Thanks so much. That's such a wonderful intro. And I'm very sorry for the delay. You know, the Moore's Law or Murphy's Law says that things always go wrong at the minute they're not supposed to. So I apologize for the internet connection problems. So I'm just gonna click on present now, and I'm gonna, hopefully that's gonna work here. Let me see. Are you able to see my presentation?
Yes, sir, we can.
You can see my screen. Okay, perfect. Okay, and are you able to hear me okay?
Yes, sir.
Okay, wonderful. So I'm going to be talking today about, so the field of control systems is obviously very broad, and I think this is a wonderful initiative that you're taking here. So, the COVID has presented many challenges, of course, but it also has presented many opportunities in terms of making the world smaller through our computer screens. So it's really a wonderful way to use this opportunity to learn about new things. And within this broad field of controls, my particular area of expertise is in trying to understand how big networked systems can be controlled and understood using tools from mathematics and control theory and so forth. So that's going to be the focus of my talk today. It's meant to be sort of at a fairly understandable level, a tutorial level. So the idea is to really expose you to some of these research ideas. And I like to keep the talks interactive. I wish I could be there with you in person, but if you have any questions, please go ahead and feel free to ask it during the talk itself. I'm not sure if I can monitor the chat room, but I'll also stop at various points to ask if there are any questions. Okay. So let me get going here. So my name is Shreyas. I'm a professor here at Purdue. I'm also one of the co-directors of our Center for Innovation and Control Optimization and Networks. So as I said, the focus of my talk today is trying to understand the problem of coordination and learning in large-scale networks. So what do we mean by this? So you can imagine these large-scale networks show up in a lot of different application domains. So for example, you could have a team or a swarm of robots or drones that are tasked with achieving a certain objective. For example, go and monitor a certain environment to look for anything strange that might be happening, or if it's after a disaster, go and search for rescue for people who are in trouble, etc. Is there a question? Okay, so and each of these agents. So also in smart factories, you can imagine you have these this thing called the industrial Internet of Things. So you have sensors and actuators that are spread out throughout these factories. In smart cities, you've got sensors that are spread everywhere, monitoring things like traffic, pollution, occupancy, etc. And of course, in social networks, you've got all these people that are connected together via different tools and apps, and even in-person communications, and they're all trying to make sense of the world, right? So in all of these applications, you've got these interconnected nodes, which the nodes could represent different things, and depending on the application, and they're all interacting with their environment and monitoring the environment and trying to make sense of the environment. Okay, and the idea here is that although each node in this network environment, no node on its own is able to understand the environment perfectly on its own. Okay, the measurements and the signals that it's getting are only partially informative. And so if the nodes want to read what's happening in the environment, they need to work together to combine their knowledge, right, their information, in order to be able to recover the true state of the world. Okay, and there are many challenges that show up here. Of course, how do you combine this information so that everybody learns what they're supposed to be doing? The network could be changing over time, right? Your friends may change over time, or if it's drones, they may be moving around. And so the network itself may be changing due to mobility. The network may also contain nodes that do not play along, right? So essentially, there may be some nodes that don't want the rest of the network to find out what's really happening in the network. This could be either due to attacks in a engineered system, so the adversary is trying to prevent the nodes from figuring out what's happening, or in a social network, it could just be people that are trying to hide something or don't want the rest of the network or the rest of the population to figure out what's really happening. So in all these settings, the goal is to formulate algorithms or dynamics to allow all the nodes in the network that are regular, that are really trying to work together to find out what's happening, to actually do that. So that's the goal. Okay, and so there are various specific instances of this problem. So I talked about a very general kind of problem, but there are specific versions of this that people have looked at in the controls community for the past couple of decades at least. So the simplest version of this is called the consensus problem. So here, each node of VI in the network, so let's call the nodes V1 through Vn, has a local static measurement. So you can think of this as a sensor, and it's measuring something about its environment, and it's a single number, right? So let's say each node is trying to measure the temperature. Each node takes a temperature measurement, and it's some number. Okay, and in the consensus problem, all the nodes have to calculate the same function of all of these measurements. So perhaps maybe you want to calculate the average temperature measurement across these sensors. Okay, and then in an opinion dynamics setting in a social network, maybe the initial measurement corresponds to your opinion about something, right? So whether a certain restaurant is good, that may be your opinion between 0 and 10, right? Or it could be whether a certain politician is good, that could be your opinion between 0 and 10. And everybody has a different opinion on the topic based on their own experiences. And maybe, you want to calculate the average opinion of the entire population. So that's an example of a consensus problem. Similarly, optimization, in consensus, everybody has a single number. In optimization, everybody has a function. So you can think of everybody as having a bunch of data, and there's some function that they're trying to minimize corresponding to that data, right? So maybe they're trying to solve some sort of regression problem, if you're familiar with that, or some sort of machine learning problem based on their data. And the challenge here is that the data is spread out throughout the network. And so the functions that each node has, which is a function of the data that they have, is also different across all the nodes, and they have to work together to calculate the minimizer of the sum of all their functions. Okay, so that's called the distributed optimization problem. Distributed state estimation is when the quantity that the nodes are trying to calculate is some sort of time varying quantity. So it could be, something that's changing dynamically according to some system dynamics, and the nodes may know the dynamical process, they may just not know the state. And so then they have to work together to identify the system state. And then distributed learning or hypothesis testing is something similar where you have a static state of the world, but each node is getting some noisy measurements, and the nodes have to work together to understand that. So these are all kind of specific versions of these problems, like I said, that people have looked at extensively. I'm going to be focusing primarily on the consensus problem in this talk, just to give you an overview of the ideas, particularly when it comes to resilience. And then at the end, if there's time, I'll talk about the distributed learning problem a little bit as well. Okay. So can everybody still hear me okay? I want to make sure I haven't dropped out here. I'm still coming through fine.
Yes, sir. We are good, sir. We are. It's audible and clear, sir.
Perfect. Wonderful. Okay. So so I'll start with the consensus and coordination problem. So here's the mathematical formulation, right? So in control theory, the goal is really to be able to analyze these problems in a mathematical way, in a systematic way. So a lot of the challenge is often in just posing it mathematically so that you can use the appropriate tools. And one of the key tools that I use in this kind of analysis that the community uses is graph theory, right? So essentially you've got these networks that are nodes interacting with each other. And so graph is sort of the hammer that you typically bring out to be able to analyze these problems. So you've got a network or a graph, G, right, with a set of nodes, V1 through Vn. So as I said, the nodes could represent whatever is appropriate for the application you're considering. In a swarm, it could be drones. It could be in a sensor network, it could be sensors. In a social network, it could be people. And we want to be able to capture the idea that nodes can exchange information with each other or send information to each other. So an edge captures that. So an edge from Vi to Vj in this edge set indicates that node Vj can get information directly from node Vi, okay? And each node I has access to, like I said, local information modeled as just a number, a scalar real value, and we'll call this xi of 0 for node of Vi, okay? So each node Vi has access to xi of 0, which is just a number that it starts out with. And the consensus problem is for all these nodes to come to an agreement on some function of their initial values. And there's lots of people that have looked at versions of this in a lot of different communities. I'm going to talk about a very simple class of dynamics here. So these are called linear iterative dynamics. And so the idea here is simple. So every day, think about it in a social network, right? So you start out with an opinion. Everybody starts out with an opinion. Every day you wake up, you talk to your friends. Okay, so you're the neighbors in your network. These are the people that you can receive information from. You gather their opinions on that day, and you just update your opinion as an average of your prior opinion and these opinions of your neighbors. Okay, so it's a very simple iterative averaging approach. Every day you wake up, gather your neighbors' opinions or values, and update your value as an average. So that's basically captured in this mathematical form right here. So xi is your value. Okay, t plus 1 at a time step t plus 1 is some weight, wii, times your own value at time step t, plus a weighted sum of your neighbor's values at time step t. Okay, so this vj and ni is basically the set of nodes that are neighbors of you. Okay, so all this is saying is take your own opinion xi of t, take your neighbor's opinions xj of t, and average them together. So the weights wii and wij all form a convex combination. So you can sort of, think a little bit about what might happen if you kept doing this, right? So every day you wake up, you update your opinion to be the average of your opinion, your neighbor's opinions. You can sort of imagine that your opinion gets closer to the opinions of your neighbors, right? And their opinions are getting closer to the opinions of their neighbors and so forth. So if you can sort of think about it, and if you think and imagine what's happening, it's not hard to see that everybody's going to eventually get closer and closer together. And you can, in fact, prove this. So this goes back all the way to a statistician, de Groot, in 1974, but a lot of work since then. And essentially, as long as the network is connected, meaning, everybody's, they don't have to be talking directly to everybody else, but as long as there's a path from everybody to everybody else, then if you were to run this over and over and over again, everybody will eventually converge to the same value. And that value will be some average of the initial values in this network. Okay? So, we can illustrate that here. So basically, all the nodes at the beginning have some spread of values. And as they run these iterative dynamics over time, so the x-axis here is the time step, the y-axis here is the values of all the nodes, you can see that they all get closer and closer together over time. Okay, so that's interesting, right? So that's a very simple dynamics, and it leads to consensus. And it may be too simplistic, right, from the context of opinion dynamics. We don't necessarily just average the opinions of our neighbors. And in fact, in society, consensus is probably not the norm, right? More often you have groups of people that have different opinions and they sort of stick to their opinions. And I'll come back to that. But these kinds of dynamics, while they're sort of a useful, very kind of abstract way to start thinking about how these things flow through networks, they are useful for things like swarms, right? So essentially, if you want to do things like flocking and you want all your robots to go in the same direction, right? So if they all start out in some random direction and you want them to all start to go in the same direction, then if you were to implement this simple kind of averaging dynamics, you can in fact get them all to start doing that. Okay, so that's a simple idea. So that's great. If everybody does it, everybody's going to converge to the same value. And if that's what you want, that's fantastic. But what happens if certain nodes don't follow those dynamics? Okay, so suppose, for example, that you even have a single node in a network that says, I'm not going to listen to anybody, any of my friends. Right? I'm just going to keep my value constant. I'm never going to change my opinion. So it turns out that if everybody else in the network does the averaging, but there's even a single node that keeps its value fixed, all of the values of all the nodes in the network will eventually converge to the value of the stubborn node. Okay, essentially the intuition is that the neighbors of the stubborn node, when they average their values with the stubborn node, they're going to get closer to the stubborn node, and their neighbors are going to get closer to the stubborn node, and so forth. And the stubborn node's never changing, so it's kind of constantly just standing there, and everybody else is coming closer and closer together. So that's a problem, right? So, and of course, we all know stubborn people in our lives. So this could be a problem if you are trying to design a system that is resilient to things like failures or adversaries, right? You can imagine, if you're trying to deploy a network of 1 million drones to go and do something, and even a single drone fails or is compromised by an attacker, all they have to do is keep the value constant for that node, and it's going to get all the other drones in the network to follow that single stubborn agent. Okay, so that's not great. So what we'd like to be able to do is design more resilient versions of these algorithms that are not so easily affected by even single failures. Okay, so consensus with adversaries has been studied for quite a long time in many different communities, ranging from computer science to controls to sociology and economics. And all these different communities are motivated by different things. So in computer science, it started out with the problem of making sure that distributed databases were all consistent, right? So essentially, if you've got data stored in different places, you want to make sure that all that data looks the same. And so if a certain database fails, you want to make sure that the other databases don't get corrupted. And so this is called the Byzantine generals problem. And this is really what motivated this consensus problem in the computer science literature in the 70s and 80s. In the control systems communications domain, a lot of this rose out of the need to do things like flocking, as I said, or solving these problems in control theoretic settings, distributed optimization, etc. And then sociology and economics, of course, you're interested in what happens with things like stubborn agents or misinformation flowing through social networks and things like that. So a lot of different insights into what factors are important and what can go wrong and how to avoid it. So when we talk about designing resilient algorithms, the first question you should ask is, what do you mean by resilient, right? So the definition of resilient is going to dictate how you choose to design the algorithm, and also what properties are required from the network and the dynamics. So some of the key questions that you have to answer when you're asking to design a resilient algorithm are the following. So first, the normal nodes, the ones that are going to do what you're going to ask them to do, what do they know? Do you want them to know the entire network topology, or do you want them to only know their neighbors, right? Only the people that they talk to? Do you want them to know what everybody in the network is supposed to be doing, or do you want them to only know what they're supposed to be doing? Right? So essentially, the more power and knowledge you give to the normal nodes, of course, you would expect the more they'll be able to accomplish. But of course, it may also be unrealistic to get them to know so much, right? So you don't know, or none of us know the entire social network that we're a part of. None of us know what everybody is supposed to be doing. All we know is our own friends and what we're supposed to be doing. Right? So, but if we knew more, we could potentially do more. Similarly, you can ask how much computation and storage do the normal nodes have? Are they allowed to do a lot of computations by storing all this data? Or do you want them to do very simple computations on just very limited data? Okay, and so ideally, you'd like them to be able to do very simple computations. But again, if you allow them to store a lot of data and do a lot of analysis of it, then maybe they can figure out more things about the network. What are the objectives for the normal nodes? Do you want them to calculate something exactly, or are you going to be okay if they calculate something that's close to what they're supposed to be calculating? In some cases, calculating something exactly is not possible, especially the guys that are spreading misinformation through the network. So you may have to settle for calculating an approximate value. Okay, and similarly, what is the model for the bad guys, right? What's the misbehavior that you're talking about? So if there are nodes that simply crash or fall out of the network because they fail, or if they get stuck at some value, right? If they keep their value to constant, and these are somewhat easier types of failure modes to handle, and these are typically just faults. These are necessarily nodes that are being careful or sneaky about the way that they're doing things. They're just going to drop out of the network or keep their values fixed. But the more sneaky key models are also possible to handle. So, for example, you can have update their values in a completely arbitrary way, and you may not know how they're going to do this. So, in this case, we call it malicious. So in this case, they're thinking carefully about how to best trick the rest of the network, and they're going to update it that way. And then an even worse version of this is called the Byzantine model, where not only can a node update its value in an arbitrary way, but it can also tell different neighbors different things. Okay, so it could tell one friend that its opinion is 9, and it could tell another friend that its opinion is 0, right? And so then by spreading this different information to different neighbors, it could try and further cause damage in the network. So Byzantine is sort of the worst case misbehavior. And then in terms of the number of bad guys, right? How many misbehaving nodes can there be? You can either be interested in tolerating, a certain number in the entire network. So this is called the F total model. So there's up to F misbehaving nodes in the entire network. Or you might be interested in tolerating up to F misbehaving nodes in every neighborhood. So each good node may have up to F bad nodes in its own neighborhood. This is called the F local model. And as you can imagine, F local is a much worse. It potentially allows a lot more bad guys in the network compared to the F total model. So these are just some of the questions that come up when you're designing these resilient algorithms, and the answers to these questions are going to dictate, how much redundancy you need in the network and what kinds of algorithms you can propose in order to be able to address these things. And there's some fundamental limitations that have been identified in different communities about the ability to overcome bad guys. So here's a very simple example, right? So suppose you have a network with 4 nodes, V1 through V4, okay? And suppose that node 3 has an initial value, which is 7, right? Let's say it's its opinion or its sensor measurement or whatever it is, its value is 7. And suppose node 1 wants to figure out node 3's value, right? It wants to calculate some function which depends on node 3's value, or it just wants to know what node 3 is thinking. But the only way for node 1 to figure out node 3's value is through node 2 or node 4, right? So node 1 isn't directly connected to node 3. And so node 3's information has to get to node 1 through either node 2 or node 4. But suppose that node 2 in this network is malicious, and it doesn't want node 1 to figure out node 3's value. So then, for example, node 2 could be malicious and pretend that node 3's value is something that it's not. For example, it could say node 3's value is 9, right? But node 4 behaves correctly and really reports node 3's actual value. But now node 1 is getting 2 pieces of information, right? One from node 2, which says that node 3's value is 9, and one through node 4, which says that node 3's value is 7. And if it doesn't have a priori reason to trust one versus the other, it's not going to know which of these values is correct, right? Should I believe that it's 9 or 7? And so in this simple network here, a single bad guy has succeeded in preventing node 1 from accurately finding out something about the rest of the network. Okay? And the problem here is that node 1 really needs a tiebreaker, right? It needs another node to be able to corroborate which of these two values is actually correct. So that intuition sort of leads to this notion of graph connectivity. So in a graph, the connectivity is the smallest number of nodes that have to be removed to disconnect the graph. So for example, on the left here, the connectivity of this graph is only 1, because if I remove that middle node that's inside that red circle, if I remove it, the graph falls apart, right? There are no more connections between these nodes. And so the connectivity is only 1. In this middle graph here, the connectivity is 2, because I have to remove at least 2 nodes to disconnect the graph. Okay, and then in the rightmost graph here, the connectivity is 3, because I have to remove at least 3 nodes. If I were to remove any 2 nodes, the graph still remains connected. So the set of nodes that that you can remove to cause the graph to not be connected anymore is called the vertex cut. And there's this classical result in graph theory called Menger's theorem, which says that the connectivity of a graph is the number of different paths between any pair of nodes in the graph. So for example, on the rightmost graph here, the connectivity is 3. And so that means between any pair of nodes, there's 3 different paths to go from the first node to the second node. Okay, so if you consider the leftmost node here and the rightmost node here, you can go from that leftmost node to the rightmost node through the top node, the middle node, or the bottom node. So you can sort of think of this as having 3 different paths for information to flow in this network. Okay, and so connectivity then is capturing redundancy of information flow, and so this is really then what has classically been viewed as the property that captures redundancy or disseminating information reliably. So the practical result is that if the malicious network, all the nodes reliably exchange information between each other, if and only if the network is left plus 1 connection. Meaning between any pair of nodes, there's at least 2f plus 1 different paths for information flow. And the intuition again is pretty straightforward here. So you can imagine, if I have 2f plus 1 different paths to send information to the network, and there's only a bad guy in the network, then at least f plus 1 of those paths must have no bad guys. So then the other node on the other end of those paths is going to get at least f plus 1 pieces of information that are all the same. And so then it can verify it. It can basically give majority voting and verify what the correct information is clear. And so this, there's algorithms that leverage this kind of redundancy in the network to reliably exchange information. So this is nice. It's sort of a fundamental classical result that talks about reliably sending information to these networks. But there are typical assumptions that underlie these kinds of assumptions, right? So the one is that the nodes know the entire network topology and the nominal dynamics of the other nodes. So essentially, going back to this idea of sending information along these different paths, well, I have to kind of know that there are these different paths so I can send information through them. And furthermore, the node at the other end has to know that I'm trying to send information to it, and it has to keep track of the information and know a lot about the system. But on the other hand, this is sort of a, if the nodes know this, then they can leverage this kind of fundamental redundancy characteristic of these networks. But the goal for us is really to switch to the other end, where you don't want the nodes to know so much, right? That still provide guarantees against adversarial behavior, but that doesn't require the regular nodes to know the entire network topology or do lots of computations. And so there you can imagine there's going to be a trade-off between knowledge and the achievable objectives. Okay, so that's what I'll talk about right now. So I'll pause there for any questions, if there are any.
Participants, please post your queries in the chat box.
If there are no questions at this point, that's totally fine too. I just want to make sure everybody's on the same page and following along. And of course, you can ask questions later. Okay, great. So I'll keep going then. And then if there are any questions, please chime in. So yeah, so as I said, what we really want are algorithms that allow us to reach consensus even when they're bad guys, but in a simpler way. So let's come back to this these averaging dynamics, right? So remember, every day you wake up, you talk to your friends, you average. Everybody at the top is going to remove their most extreme neighbors on either end. So they're going to remove a 1 and a 0, and then average the rest, and they're going to stay 0. So you can see in this graph, when everybody throws away highest and lowest and averages the rest, none of the values change, right? Nobody ever changes their opinion. And this is because they're essentially throwing away the opinion of their friends from the other community, right? And everybody else inside their community has the same value. So this graph is very dense, right? So there's lots of edges. Everybody's connected within their own community, and they have all these edges to neighbors across the, in the other community. But even though this graph is so dense, so highly connected, just throwing away highest and lowest is preventing consensus in this network. Okay, and so what we want to do is try and figure out, well, what is it about this graph that's preventing that kind of consensus? And so the idea is that although each node has a friend in the other community, they don't have enough friends in the other community, right? So they're essentially throwing away all of the useful information that they can get from the other community. So each node here has only one friend in the other community, and if they're going to throw away highest and lowest, it could be that friend's opinion, which is unfortunately getting thrown away. So this kind of classical notion of connectivity captures the idea that together everybody has enough friends, and this graph has that property. But when you're doing these kinds of local dynamics, local decision making, what you really want is a property that captures the idea that each node on its own has enough friends in the other community. You want to make sure that there's some node that still retains some information from the other community after it throws away extreme values. Okay, and so what we really need is a new topological graph property to be able to characterize conditions under which these kinds of dynamics will succeed. So, so we basically come up with a new graph condition to do this. And so let me explain this graph condition. It's a pretty simple one, and it's easily explained through an example. So suppose I give you a graph and I consider a set of nodes, right? So some subset of these nodes. We say that that set is R reachable if that set contains a node that has at least R friends outside that set. Okay, so let's just do an example here. So this green set at the top here, okay, so this green set has a node that has at least 3 neighbors outside that green set, right? So for example, node 5 has 3 neighbors outside that green set. So this green set is 3 reachable. It contains a node that has at least 3 neighbors outside that set. Similarly, this pink set at the bottom here is 4 reachable because it has a node that has at least 4 neighbors outside that set. So B7, for example, has 4 neighbors outside that set. So R reachability captures the idea that there's some node in this set that has at least R neighbors outside, it has enough neighbors outside that set. Okay? So this is a graph property. This is a set property. What we really need is a graph property. And so graph, we say, is R robust if no matter how I choose 2 different sets of nodes, at least one of the sets is R reachable. Okay, so for example here, no matter how I choose 2 subsets of nodes, let's say I pick the pink set and the green set, at least one of these sets is 3 reachable, meaning at least one of these sets has a node that has at least 3 neighbors outside the set. For example, node 1 has 3 neighbors outside the pink set. Okay? So you can check that no matter how you choose 2 different sets of nodes, this property holds. And so what is this property? It's basically, remember, we were trying to avoid the situation where we were able to take the graph and split it into 2 sets where no node in any of those sets had enough neighbors outside its own set. This R robustness property is basically trying to address that problem. So it's basically saying no matter how you split the graph into 2 sets, one of the sets is going to have a node that has enough neighbors. Okay, so hopefully that definition is clear. And so then the key result is basically the following. So if the network is 2f plus 1 robust, then if you were to run those local filtering dynamics, right, where everybody removes the highest f and averages the rest, then no matter what any f local set of Byzantine nodes do, so f local meaning you can have up to f bad guys in every good guy's neighborhood, those could be Byzantine, so they're worst case adversaries. They can pretend to be the friends for a while and then stab in the back, or they can spread misinformation. They can tell different friends different things. You can have absolutely worst case behavior, and you can have an F local set of those. And even with that, if the graph has this kind of robustness property, if you were to run this kind of local filtering where you ignore extreme values at each time step, the bad guys cannot prevent the good nodes from reaching consensus. And that consensus value is guaranteed to be in a certain moderate range. It's guaranteed to be between the largest initial value of any good node and the smallest initial value of any good node, okay? So the bad guys can't prevent consensus, and that consensus value is guaranteed to be in a moderate range, okay? So the key takeaway point here is if the graph satisfies this kind of required robustness property, then these local filtering algorithms are very simple to implement, right? The nodes don't need to know the entire network. All they need to know is their neighborhood, and they just throwing away extreme values is very simple, but it still provides very strong guarantees against adversarial behavior. So here's just an illustration to give some intuition about what can happen, right? So the bold red and pink lines in here are essentially the adversary's behavior. They can do anything, but here I've just shown them doing some sort of random things. But if they were to choose their values to be very large or very small, they know they're going to get thrown away by their neighbors. And so the values that they can choose for themselves or that they choose to send to their neighbors have to be in some sort of a moderate range, right? Because otherwise they're going to get thrown away. And so all these thin lines are the values of the good nodes. And you can see that those values of the good nodes are getting closer and closer together. So what the bad guys can do over time also gets squeezed, right? So they can't choose too extreme values because they'll get thrown away, and the range of values before they get extreme also gets smaller and smaller because everybody else in the network is converging to consensus. So this is just an illustration to show that why the bad guys can't really prevent consensus in these settings. And then the other question that comes up then is, well, okay, you need this graph to have this robustness property in order for this kind of guarantee to hold. But we looked at that graph, which seemed to be pretty nice. It had a lot of edges, and in that graph, it didn't work. Right? So that graph didn't have the required robustness property. So you could say, well, you're telling us this algorithm is good, but it really requires the graph to have that property, and maybe that property is too strong. Maybe you're asking too much from the graph. So that's what we were worried about as well. And so what we did was we looked at variety of models for large-scale networks. So when you're trying to think about these, huge networks like Facebook or the power grid or anything else that has millions of nodes, you need some sort of mathematical model to be able to capture those networks because you can't just physically grab those networks and analyze it, and they're always changing over time. And so there are these things called random graph models for large-scale networks, where you sort of randomly create these networks and you choose the randomness in such a way that it has certain properties that are shared by these real networks. And it turns out that if you were to look at many random graph models for large-scale networks, these random graph models tend to have this robustness property sort of pop up for free. It was something that we had not realized before because we didn't even know to look for this property. But when we started looking for this property in these random graph models, it turns out sort of very surprisingly to us that these random graph models do in fact have this property under certain parameter ranges. So what that really means is that although this property is strong in that you can create graphs if you carefully create those graphs so that the graphs don't have that property, but if you were to sort of randomly consider graphs, then this property tends to show up in those networks. And so what that means is that although this is a strong property, it does seem to be prevalent, surprisingly, in many of these networks. And so that seems to indicate that these kinds of algorithms may be quite promising to implement in some of these large-scale networks. Okay, so let me just summarize that portion of the talk then. So the key thing here is that if you're talking about resilience, you have to first define resilience, and sort of some of those questions that I posed are going to be quite relevant. But when you're talking about resilience, you need to have some sort of redundancy somewhere, right? And typically it's in terms of the graph properties. And the specific nature of the redundancy depends on what you're trying to achieve. And for this kind of local filtering, very simple dynamics that I talked about, it has a lot of promise for achieving this kinds of resilient consensus with very simple algorithms. But it requires this new notion of redundancy in networks, this kind of 2f+1 robustness property. But this local filtering dynamics is very promising, and it actually holds promise for a lot of different applications outside of just consensus. Okay, so I'll stop there for a minute to answer any questions that people might have.
Yes, comment section has some questions you can view.
Perfect. Okay. Let me see here. Okay, so why a node? So why should a node never use a value from its opposite set, and what is f total and f local? So if you remember, f total means that in our network there are at most f bad guys. F local means that in any neighborhood there are f bad guys. So f local means that everybody could have up to f bad guys in their friends, whereas f total says that in the entire population there are at most f bad guys. Hopefully that helps, right? So the f local model potentially allows a lot more bad guys in the entire network because everybody's allowed to have up to f bad friends. And then